Well, thank you, Jibin, for the nice introduction. It's a great pleasure to be here. I guess we have a full room. Hopefully you'll be able to see the slides from the back. It's a bit...
Yeah, because we have a screen there.
Oh, there's a screen there. Okay, yeah, that's smart, yeah. That's a good principle of locality, right? There's distance, and to tolerate the latency, you put another cache over there, or replicate the data. Thank you. Thank you for inviting me. It's a great pleasure to be here in China again. This is my third time this year. And now that I have a 10-year visa, I can come for much more easily. Yeah. And this is my first time in Zhuhai, and it's nice to be by the coast for sure. Okay, I'm going to talk about intelligent architectures for intelligent machines. I like this title a lot. Actually, it's not. I should attribute the credit to someone else because I was invited to give this talk at SRC, Semiconductor Research Corporation, in one of the keynotes in their funding meetings, and I was too late to supply my title for the talk. And the person who invited me decided that I should be talking about architectures for intelligent machines. So they put the title as Architecture for Intelligent Machines. I said, this is a great title. I could use it, but it's missing something, which is really this intelligent part at the top. So I added the intelligent architectures for intelligent machines, and I've been now using this title for some of my talks. And if you actually have a title like this, you can talk about anything, right? That's the beauty of this, I think. Now I'm going to talk about anything in the end. Now, hopefully, I'll give you examples of why we chose this title in the end. But hopefully, nobody will dispute this today. Today, we're doing computing. Computing is everywhere in our lives, and it's really bottlenecked by data. In the end, what we're doing is bottlenecked by how fast we can analyze the data, how fast we can store the data, how fast we can access it. And data is really key for many applications. Today, artificial intelligence, machine learning, those are the hot applications, and they're going to be hot. But there are going to be a lot more applications that are coming, like genomics that I will briefly talk about. They're all dependent on data, and we're producing data much faster than we can consume, actually. These applications require rapid and efficient processing of large amounts of data, and data is really increasing. As I said, we can generate more data than we can process. And these are some applications that are very much dependent on data. You can call these traditional applications. They're very important. They actually are at the base of many, many applications that we develop. Graph processing is, for example, at the core of many machine learning algorithms, networking algorithms. I'm not going to go through these in detail. We'll touch upon them during this talk. But if you look at them, data is the performance and energy bottleneck in these applications. If you look at the mobile end, I don't want to call this the lower end because some of the highest performance processors are being designed in these SoCs today. Again, the applications that we are using and heavily relying on are also dependent on data. And data is, again, a performance and energy bottleneck in those applications. Now, if you look at some emerging applications, this is genomics. Oh, thank you. I have redundancy in water now. That's good. We do a lot of work in genomics, actually, and this is a fascinating field. And this is an example where we can generate a lot more data than we can process. This is actually, if you see it over here, this is a figure that we commonly use in genomics. This is basically showing the cost of sequencing a genome. And it's been dropping, as you can see, much faster than the cost of a transistor has been dropping, which is this line over here. As a result, we're able to now produce a lot of genome data. Of course, we're not able to analyze it all in the ways we like it. But this is very important, I think, going into the future. We can sequence genomes really well, but the computational bottleneck is a big problem because we want to do a lot of analyses on it, but it just takes too much time to do the analysis, especially if the analysis is very latency sensitive. Like you want to make a very quick decision as a doctor to actually administer a certain drug or something like that, right? And data is, in the end, a performance and energy bottleneck in these applications also. And I'd be happy to talk about this further, but we're doing a lot of work in genomics. This is one of the recent devices that was introduced 5 years ago by Oxford Nanopore. You can buy this device for relatively cheap. You can do your sequencing, and people are using this device, for example, in Africa today to sequence viruses. But what they're doing is, because they don't have computation capability and storage capability inside the device itself, they're actually sending all of the data that they produce to data centers across Europe, China, US. So they're causing a lot of data movement all over the world to be able to analyze this data. And even then, you're not able to get the analysis that you want because you cannot do the iteration very quickly in the end. So this is an example of the way we're building architectures today, in my opinion, that are not very intelligent, right? We have a lot of intelligence in the device. The device itself can actually get us a lot of data, but because we are designing architectures the way we are, we cannot analyze that data really well. As a result, I will not call this architecture very intelligent in the end. And this is an example of the macro level data movement, like global data movement that we're causing in the world. I'm going to focus a lot more on the micro level, but it's the same mindset in the end. We have this mindset that seems to design systems that lead to a lot of data movement, a lot of churn in the system. And hopefully we would like to eliminate that in an intelligent architecture. That's one example. Okay, I'd be happy to talk about this further. Okay, so if you look at all these applications, in the end, data overwhelms modern machines. Basically, it overwhelms the storage and memory capability. It overwhelms the communication capability. And in the end, it bottlenecks the computation capability. You may put a lot of computation in your device, but if you're not able to store it or communicate it to the processor, then you have a problem with the computation capability as well. And in the end, data storage and movement greatly impacts robustness, energy, performance, and cost, all of the metrics that we really care about when we design a system. And I'm going to show you examples in this talk. So when you look at a computing system, it actually consists of 3 key components. If you go back to the fundamentals, you need to compute, you need to communicate, and you need to store. And if you look at all of those, we've heavily optimized the computing unit today. So our focus has been the computing unit, and we've kind of ignored the rest. And that's part of the reason why we have a not so very intelligent architecture today. And as a result, the systems we design, this is a general purpose system. This is a picture that I drew in 2008, actually. It's still the same. I was writing a proposal to NSF at that time, and I wanted to draw a nice picture. I still use this picture over here. But basically, if you look at a system that we design today, most of the system is really dedicated to storing and moving data. We call this a computing device. But if you do the calculations, more than 90% of the real estate, hardware area of the system, and the cost of the system actually, cost is a bit different, but still most of the cost of the system is dedicated to storing and moving data. So it's good to think about this a little bit. We call this a computing device, a computer, right? But most of it, what it's doing is really storing and moving data. Okay, so this is because data overwhelms modern machines in the end, right? And we've done a lot of analysis and a bunch of workloads. I'm going to give you one data point over here. This is one work that we did with Google over the course of 1.5 years. We analyzed the applications that I showed you over here, which everybody is using in some form. These are, of course, Google's applications, but they're also applications that you use in other devices, clearly. And we found out that more than 60% of the entire system energy in an SoC like this is really spent on data movement across the memory hierarchy when you run these applications. And this doesn't sound very good, of course, right? Hopefully we'll find architectures to eliminate this. So basically my axiom in this talk is an intelligent architecture has to handle data well today, because data is really what we are dealing with in modern systems. So the question is, of course, how do you handle data well? And I have 3 bullets over here, which we're going to go through during this talk. First of all, I believe we need to ensure that data doesn't overwhelm the components that we design. So how do we do that? We need to, I believe, have intelligent algorithms to minimize data movement. We need to have intelligent architectures to minimize data movement. And I think it's just a system design problem, not just our algorithms, not just architectures. We really need to design the whole stack, algorithms, architectures, and devices such that we minimize the data movement that we have in the system. Second, we should take advantage of the vast amounts of data and metadata that we have in the system today. We're not doing so good on this task. Basically, there's a lot of data that a system sees over its lifetime, or even the last second. And we should use it to improve architectural and system level decisions. I'll give you an example. This system, I've been using it for 5 years, let's say. Actually, I have been using it for 5 years. It's old right now. It has algorithms that are baked in its hardware, in the memory controller, in the cache, in the processor. And this system, over the course of 5 years, it's seen a lot of applications, a lot of usage models, a lot of frustration from me. And it hasn't learned anything. It's still using exactly the same algorithms that the hardware designer put inside it, right? So this is not an intelligent architecture in the end. If you look at humans, right, we learn in milliseconds, right? You actually quickly adapt. And that is not present in existing architectures, as you can see. So this, I think, it needs to be changed if you really want to design intelligent architecture going into the future. And the last one is, I think, also important. We should really understand and exploit the properties of different data. Today's architectures are designed such that they don't distinguish different types of data much, at least the general purpose architectures. In special purpose domains, sometimes we actually distinguish data, but that's very special purpose. General purpose architectures, most of the data you don't know much about, basically. But if you know some things about the data, for example, the properties of how you can compress it, how you can approximate it, how much security should you provide, How much reliability, unreliability can you tolerate on this data? So there are lots of properties that you come up with for every piece of data element. If you can somehow communicate that to the architecture and the system overall can make much better design decisions in terms of how we can treat that data. So this talk is going to touch upon all of these. I will actually focus a lot on the first part, but spend some time on the second and third parts as well. Does that sound good? Okay. It's a bit warm here, so hopefully people are not overwhelmed. And I usually talk relatively fast. One suggestion that I have is don't try to read everything that I have on the slides. Instead, try to follow me. That's easier to understand that way. These slides are all going to be available at some point online. Okay, so basically, given what I said earlier, the corollaries is this. Today's architectures are really terrible at dealing with data because they're designed to mainly store and move data as opposed to compute. Because they're designed with the processor-centric paradigm as opposed to data-centric paradigm. So I'm going to talk about this and spend more time on this. The second corollary is today's architectures, again, are not good at taking advantage of vast amounts of data and metadata that they see over the course of seconds, milliseconds, years, decades. They're designed to make very simple decisions, ignoring lots of data, because they're designed the decisions are made in a human-driven manner as opposed to a data-driven manner. Some human designs the policies and they decide this is the policy, as opposed to policy changing over time based on the data that comes into the system. And the last corollary is that architectures today are terrible at knowing and exploiting different properties of application data. They're designed to treat all data as the same, for the most part. This is because they make component-aware decisions as opposed to data-aware decisions, and this is going to become very clear. For example, when I make when I design a cache, the cache really makes decisions into itself because it doesn't know the properties of different data. Okay, so we're going to start with the first one over here, which is really data-centric or memory-centric architectures. So the question is, of course, if you want to design a data-centric architecture where data is the first-class citizen, what do? I believe these are at least 4 properties. I'm going to especially talk about the first part, which is processing data where it makes sense, where it resides, processing close to where the data is. But I will also briefly talk about this just right now. If we have time at the end, I'd be happy to talk about this latency issue, because this is really important in my opinion. Basically, if data is really important, we need to provide very low latency and low energy access to data, which means that we need to build memory that's low latency and low energy. But if you look at the memories that we build today, DRAM, for example, that's where we house most of our data, it's really not designed for latency or energy. It's designed for capacity, which is important, but it's mainly designed for capacity. As a result, its latencies are too long. Its energy is also too high. But if you actually change the mindset slightly, such that latency is also a first-class citizen, then we can actually get to a point where the access to data is much faster. On top of this, of course, we need low-cost data storage and processing. I'm not going to talk about that. And intelligent data management, which is actually related to processing data where it resides, but slightly different. But I'm going to focus mainly on the first part over here. So let's jump in. I call this processing data where it makes sense. Basically, this means that we should really process data where we can minimize the data movement and energy and latency to access the data with. Today, we have only one choice. We process in the processor. Maybe we should be processing in a distributed manner across all parts where the data is. So clearly, this idea is not new. This idea is actually very old. In-memory computation, the first concepts, at least in the published literature, were developed in the 1960s. The first paper that's general purpose is by Harold Stone in 1970, IEEE Transactions on Computers. It's called a logic in memory computer. And later, people have published papers in the 80s, 90s, so in the database community, for example, in the 80s. David Elliott Shaw has a beautiful paper on the non-1 database system. But this idea never materialized. Actually, never materialized, let me put it that way, even in special purpose domains. But today, I think we have a big opportunity because we're really bound by data. And there are 2 reasons for it. I'm going to give you the first reason very quickly. I'm going to focus on the second reason over here more. Basically, we are having a lot of problems with the technology that we design memory systems with. And it's DRAM today. And DRAM scaling is having a lot of problems. I'm going to give you examples of this. As a result, industry is very much open to new memory architectures. Controllers are being put close to DRAM. And industry is designing architectures that look like this, 3D stack. Basically, you have a logic layer underneath memory layers. And you can actually do computation inside the logic layer. This is an example. Actually, monolithic 3D architectures are under development. There are actually startups that are doing even more aggressive things. They're actually putting processing units inside the DRAM chip. UPMEM is one startup that's doing that. Micron has been experimenting with relatively simple operations inside the chip itself also. And this is happening because we're having problems with memory scaling. This is actually a paper that I wrote in 2013, invited to the International Memory Workshop. I'd be happy to talk about it also. And at that time, we were arguing that memory scaling issues are real, and it's going to get worse and worse. And I delivered the talk. At that time, we didn't have a lot of evidence. And later, actually, this is a paper that we wrote recently. It was published in June 2019. And we can talk about real evidence in the field that shows that memory is becoming less and less reliable because scaling is just hard. It's just too difficult. And very briefly, I will talk about the story of Rowhammer. This is one example of the scaling problem that we have in memory chips today. Essentially, because cells are too close to each other, you can predictably induce bit flips in commodity DRAM chips. Because whenever you access one row, you're really affecting adjacent rows, physically adjacent rows, because there's not enough electrical isolation between the rows. And this is just one example of the scaling problem. And we found out that more than 80% of the tested DRAM chips are vulnerable. And this is really the first example of a simple hardware failure mechanism, circuit level, that can create a widespread system security vulnerability. Because you can cause a bit flip in a predictable manner in some bits, somebody can take over your system. So it really threatens the basics of what we build computers on top of. And as a result, people are writing articles that look like this. Forget software. Now hackers are exploiting physics. I like this one because this is written by a Wired reporter. And I think this really gets to the heart of the issue. It's really about a physical problem that's going all the way to threaten the security of systems that we design today. And this is one example graph that we have shown in our paper that basically shows that DRAM modules that are manufactured recently, when the paper was written in 2014, are much more vulnerable to this sort of Rowhammer effects, scaling problems, basically. Basically, all of the chips that we tested that were manufactured between 2012 and 2013 from all major manufacturers exhibited these Rowhammer errors. But before, it was not a problem because the cells are large and you don't get these bit flips in memory. So this is going to become much worse and worse into the future. Of course, right now, people are aware of the problem and people are going to try to solve the problem at different ways. But other problems will start appearing. So we will have a lot of issues with technology going into the future. When we actually wrote the paper, the Rowhammer paper, the first thing that we said was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. This is very fundamental. I think that's absolutely true. I don't think there's another way of building a system without these properties. If you know of a way of building a system without these properties, please let me know. I think you may win the Turing Award if you actually do that. And actually, we said that you could you could hijack a computing system if you're able to do this. And Google folks at Google Project Zero showed that with exploiting these bit flips, you can take over a system. You can actually gain kernel privileges with a user-level program. I'm not going to go into more detail on this one, but this is an example that's showing the seriousness of the problem. Basically, you have these bit flips that are real out there in real DRAM chips. People may be exploiting it actually. You don't want people to be exploiting it clearly. So how do we solve the problem? The solution is really you need to have some sort of intelligent controller. Because all of the other solutions that you actually put inside the DRAM chip are extremely costly. And I'd be happy to talk about that separately. But if you actually make your controller slightly intelligent, then the controller actually can anticipate some of these problems, can actually online correct some of these problems much more easily than designing a device that's actually robust to all of these issues. So this is one reason why we need intelligent controllers from the bottom up, meaning circuits are not reliable. So we actually should really design the architecture such that they're more intelligent. And of course, there are other examples, like refresh is another example. That's really the scaling limit of DRAM. For example, this device right now is wasting a lot of power because it's refreshing its DRAM. It has to refresh its DRAM for various reasons. And it's going to become worse and worse as this technology scales into the future. But if you actually design an intelligent controller, the intelligent controller actually can get rid of a lot of the refreshes that are happening right now. Because most of the time, you don't need to refresh memory as much. But because our controllers are not intelligent, they don't know how often which cell needs to be refreshed. They're refreshing everything every 32 milliseconds right now, actually. It used to be 64 milliseconds when I was giving this talk 5 years ago. Now it's 32 milliseconds with LPDDR4. OK, so that's the circuit level perspective. But we also have a big pull from systems and applications. That's the top-down perspective. Basically, today, data access is a major system and application bottleneck. Systems are energy limited, and data movement causes much more energy than computation itself. I'm going to go into all of these in a little bit. And as a result, systems are demanding us to do something different. Basically, be intelligent about how you handle the data inside the memory. In my opinion, I think this is actually maybe a longer-term perspective, but I think the question is like this. Do we want a future that looks like this, that's beautiful, clean? Or do we want a future that looks like this? Or maybe even worse than this, I don't know. It's possible, right? I think basically, I don't think I want this one. But I would like certainly something that's energy efficient and sustainable. But I don't want to give up performance also, right? Because there are a lot of important things that we want to do. We actually really want to be aggressive in terms of how we improve performance. But we want high performance to come with energy efficiency and sustainability. The question is, how do we achieve all of these three things that seem to go against each other, right? I think that we should really realize the problem. The problem is really data access is the major performance and energy bottleneck today. And our current design principles essentially cause great energy waste. They also cause great performance loss, and I put this in parentheses. They cause great energy waste because we're moving data all around the system, as I said earlier. So that's wasting a lot of energy. It's also wasting performance, but we actually design our systems for performance. So what happens is we actually put a lot of complexity into our systems to overcome the performance issues with data movement. Like we add caches, we add multi-threading, we add prefetching, we add all sorts of memory hierarchies that are actually huge, and they actually add a lot of complexity into the system. When they work well, but most of the time they actually don't work in real applications, and as a result, what they cause is additional complexity, and they cause even more energy waste. So today we're in this vicious cycle, and that vicious cycle is data movement is a problem. It causes performance issues. It causes energy waste. To overcome the performance issues, we add more complexity and we cause even more energy waste. So we keep circling in this vicious cycle. Of course, if you want to design a more intelligent system, get rid of all these issues, you really need to break the vicious cycle. If you want to break the vicious cycle, I think first of all, we really need to understand how do we break, what is the problem? And the problem is this, in my opinion. Basic processing of data is really performed far away from the data. And if you look at the picture that I showed you earlier, I'm not going to dwell on this. There are three major components: computation, communication, and storage. We've heavily optimized the computing unit over here. Today's systems are very processor-centric or accelerator-centric. It's the same thing from my perspective. All data has to come to the processing unit, computing unit, to be processed. This happens at great system cost. Data goes around a lot. And as a result, data storage units are actually dumb and they cannot do much. So I believe we need to really change this. And we know that actually the problem is really memory. This is actually a quote from Dick Seitz, who designed some of the fastest processors of its time, alpha processors. And he wrote this one-page article in Microprocessor Report in 1996. I would recommend everyone to read this, actually. It's a beautiful article. And the title is this, basically. It's The Memory Stupid. And he basically says that we designed this processor to be the fastest of its time. It's able to finish 4 instructions every cycle. But on this important workload that we really designed it for, it's finishing 1 instruction every 4.7 cycles. Essentially, it's operating at 1/18th of its peak bandwidth. Why? It's waiting for data. And he basically says, this is a person who dedicated his life to designing processors, fast processors. He basically ends the article saying that, this is the sentence directly copied from the article: I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. I think that's a very good ending. Okay, if you don't believe me, I've actually done some studies on this. This is data from my own PhD thesis, run-ahead execution. We actually analyzed workloads that Intel was using to design its processors with at the time. And we found out that most of the time the processor is waiting for data. Very similar to what he has observed, basically. Nothing has changed in the course of 10 years over here. Okay, you don't believe Dick Seitz, you don't believe me, fine. Since, although I'm in China, I should be careful. Most people believe Google. In most of the world. Or maybe you believe Baidu here, fine. I think Baidu has published similar studies, maybe not to this detail. But basically, Google has published a study in 2015. It's a beautiful paper in ISCA 2015. And they basically analyze all of their workloads in data centers. And they show that the top-of-the-line processor that they're using in their data centers is waiting for memory most of the time. More than 50% of the time, the processor is waiting for memory. Only 10 to 20% of the time in all of their data center workloads, according to what they say in the paper, the processor is finishing instructions, meaning doing useful work. So I've given the history in the course of 20 years or so, and nothing has changed. The processors have become faster, but they're still waiting for data. They're wasting energy, and they're wasting, essentially, performance because of that. Okay, I'd recommend that Google paper. I think it's cut off over here, but you'll have the slides. Essentially, the reason is we have a processor-centric design. We have a grossly imbalanced system. Processing is done in only one place. As a result, data moves a lot. And this is energy inefficient, low performance, and complex. And to overcome this, we actually bloat the processor and the accelerators. We actually add complex hierarchies and mechanisms that makes things even more energy efficient, low performance, and complex. I say low performance because even though we add all of this stuff into the system to improve performance, if we didn't have to move the data in the first place, we could have actually had much better performance to begin with. We could use that real estate for something else, right? Okay, as a result, we have this picture that I showed you. Most of the system is dedicated to storing and moving data. Maybe that's not a good picture. So if you look at the energy perspective, it's even worse, actually. This is a slide that I borrowed from Bill Daly from his high-peak keynote. You could argue with the numbers because these are relatively old numbers, but the trends are very similar in the end. I'm going to give you more up-to-date numbers in a little bit. Basically, he analyzes the cost of energy for different operations. A 64-bit double precision floating point operation, 20 picojoules. It's a complicated operation, actually, in today's systems. A DRAM read or write, 16 nanojoules. That's 800x. Okay, I'll take the liberty to make it 3 orders of magnitude. But basically, if you look at the numbers, it's between 2 to 3 orders of magnitude. A memory access, a single memory access, consumes 2 to 3 orders of magnitude more energy than a complex addition. Now the question is, of course, if you want to add two numbers and store the result, that's 3 memory operations, and you don't have good locality in these numbers, do you really want to bring all those 2 numbers, do the addition, and store the result back into memory, doing 3 memory accesses to do a very simple, in terms of energy, floating point operation? I would say no. Okay, you don't believe the 100,000x number. There are other numbers that show that it's about 100x. Actually, I was in the DAC Design Automation Conference in June, talking about the processing in memory also. But there was an AI accelerator session where people were talking about their AI accelerators or machine learning accelerators. And some people were giving out numbers. And one person gave out the number 160 times. That was the cost of a DRAM access in their AI accelerator compared to a floating point multiply and accumulate. 160 times. It's not 3 orders of magnitude, but it's more than 2 orders of magnitude. So that's a lot. As a result, we have a picture that looks like this. More than 60% of the total system energy is spent on data movement in traditional applications like web browsing, video processing, and also machine learning inference like TensorFlow. I'm going to give you a little bit more detail over here when we get to it. Essentially, I will argue that we do not want to move data because data movement is very costly in terms of energy, even if you ignore performance. So we need a paradigm shift to actually enable computation with minimal data movement in our systems. Compute where it makes sense, where really the data resides, and where it really makes sense to keep the data local without actually moving it much. This requires, I believe, making computing architectures more data-centric, essentially changing the paradigm from processor-centric to data-centric in the end. Okay, let me give you an example of this. An example of this is processing in memory, clearly. I think memory is very important because memory main memory enables lots of data storage at really reasonably low latency, even though we can improve the latency. But I think what I'm going to suggest can be applied to many places. You could do processing inside the caches. You could do processing inside the register files, if the register files are large, for example. You could do processing inside the storage. You could do processing inside the tape. And I think we should really be considering all of that in our systems. But I'm going to focus more on the main memory side. I believe main memory side is a little bit harder in existing systems because there is a very rigid interface between processor and memory. And there's a huge processor and memory dichotomy that we really need to break going into the future. So what does processing in memory entail? Basically, you put a lot of your important data inside memory. And you basically query memory, ask questions to it. Memory, can you do this operation on this data for me? Memory can say yes or no. Or maybe memory can talk to you intelligently and say, I can do it five minutes later if you can wait for 5 minutes, right? We need to have this intelligent conversation with memory. Today, we don't have that. We basically dictate to memory, I'm going to read from you, I'm going to write to you. That's it. We cannot do much other than that. But if we can query memory and talk to it and offload functions to it, the memory can perform those functions and return the results. And then maybe we'll have a handshake. We'll figure out how to best execute a particular application or query over time, right? So clearly, there are many, many questions related to this. How do we design the compute-capable memory and the controllers, the processor chip and the in-memory units, the software and the hardware interfaces? These are actually really important. None of those exist in the forms we like today, but we need to do that. The system software compilers and languages to enable this. And I think in the end, algorithms and also theoretical foundations, algorithms are very important actually, but even theoretical foundations, if you, most people here are probably computer science majors, or even if you're electrical engineering, it doesn't matter. At some point, you probably have taken a theory of computing course. And if you look at a theory of computing course, implicitly, all of the assumptions that we make in that course are really about processor-centric. Basically, we don't think about data as a first-class citizen. All of the theory of computing was developed with the processor-centric paradigm because that's how the processors were designed at the time. We don't think about the data movement when we analyze algorithms, for example, for the most part. Certainly not in courses. I think we really need to rethink the theoretical foundations on computing if we really want to be data-centric in the end. So, of course, this is very aggressive, right? In the end, we really need to examine the entire stack if we want to take full advantage of processing in memory or processing data where it makes sense. But I'm going to show you examples that we could get there step by step. But I think this is very fascinating because we could do research all across the stack, spanning all the way from algorithms to devices. Maybe even electrons, but my background doesn't allow me to think about how to make electrons more data-centric. I think physicists can think about that better probably than I can. Okay, so given that, I'm going to talk about two different approaches to processing in memory. One is millimeter-changing memory chips, and the second is exploiting 3D stacked memory. There could be other approaches also that I'm going to cover over here, but I'd be happy to talk about that separately. Let's talk about the first one over here. First one is very interesting because it has not been examined a lot until very recently. And I'm going to give examples of what's very recently. So basically, whenever you design memory, memory actually has capability to perform data movement internally and also perform computation internally if you make some very small changes to memory. Today, we don't do it, but we can easily do this. Basically, we can exploit the internal connectivity to move data. We can exploit the analog computation capability that exists in many, many memories. I'm going to give you a bunch of examples over here. And I'm going to start with cheating. I'm not going to even talk about computation. I'm going to talk about data movement, essentially data copy and initialization. And data copy and initialization is used in many, many applications. Like, for example, when you start out a database, let's say terabytes and terabytes, you initialize it to 0, right? Or some value. And that consumes a lot of time. That's a very simple example. There are much more latency critical examples potentially in virtual machine cloning and duplication, for example. I'm not going to go into. But there are a lot of applications that use data copy and initialization. And again, if you don't believe me, since most people believe Google published this paper that talks about their data center workloads. And in their analysis, they showed that about 5% of the entire execution cycles in all of their data center workloads is spent on just 2 function calls, memmove and memcopy. And this is not the source of all of data movement, clearly, just 2 function calls. This sounds bad, right? 5% is a lot for 2 function calls. Okay, so how do we do the data copy today? Basically, we're not very intelligent. If we want to copy a source page, the white page over here to this gray page, we basically go through the memory. I'm not going to go through the details of it, but we basically go through the processor. We basically disturb everything inside the system to be able to do this copy. We bring the source page byte by byte, we bring the destination page byte by byte, do the copy, and write back the destination into memory. So 3 memory accesses. Assuming that this is 4 kilobytes, it's 12 kilobytes of data movement. If this is 1 megabyte, this is 3 megabytes of data movement, right? So this is high latency, high bandwidth utilization, obviously. Cache pollution, but you could eliminate that by doing this through the direct memory access engine. And it causes a lot of unwanted data movement because maybe you're not going to touch that data for a long time, especially if you're initializing a large data structure, for example. So if you do this copy, a small copy, 4 kilobyte page copy, through the direct memory access engine without even touching the cache hierarchy, with some technology assumptions, it costs about 1,000 nanoseconds and 3.6 microjoules. Now, if you actually took this picture to a child, sometimes it's good to think like a child, and ask the question, am I doing something wrong over here? Probably the child will tell you, this sounds stupid. Why don't you just do this, right? Move the data inside the memory, right? And I think we need to really think simple going into the future, examine all of these design decisions. So if we are able to do this completely in memory without disturbing anything else in the system, clearly this will be low latency, low bandwidth utilization, no cache pollution, and no unwanted data movement. Essentially, I'm going to show you a mechanism that takes us 1,000 nanoseconds, brings it down to 90 nanoseconds. Actually, if you optimize it, you can go down to 70 nanoseconds or so, and 3.6 microjoules to 0.04 microjoules. And the idea is actually very simple. Basically, the high-level concept is this, but of course, you need to go down into the details of how you do it. And the detail is called row clone. We published this paper in 2013. It was rejected once before it was published. I'm going to talk about that also. I think there are a lot of students over here, so they will appreciate, hopefully, what I'm going to talk about a little bit. But basically, the idea is very simple. If you have 2 rows, both of the rows are in the same subarray in DRAM. They share sense amplifiers. You want to copy the source row to the destination row. You just need to do 2 consecutive activates. You first activate the source row, which brings the data into the row buffer, just like existing DRAM operation. The next thing you do is an activate to the destination row. You basically you kind of violate the existing DRAM operation. You activate the destination row, which implicitly closes the source row, connects the sense amplifiers to the destination row, and once the sense amplifiers connect to the destination row, the data that you captured from the source row in the sense amplifiers drive the destination row, because sense amplifiers are much stronger than the cells themselves. Essentially, what we're doing is we're using the sense amplifiers as a buffer to buffer the source data, source row, and then move it to the destination row over here. That's the idea. 2 consecutive activates. You could almost do it in existing DRAM chips. And in our paper, actually, we said that this is very negligible hardware cost if you want to do it reliably. I'm going to get back to this. 5 years later, some folks from Princeton showed that using our infrastructure, they showed that actually you could do this in most existing DRAM chips without actually changing the DRAM architecture. So we didn't show that, but they get the credit for showing that in real DRAM, in off-the-shelf DRAM chips that you can buy today. Okay, it's not surprising to us, but I think it's good that people are showing this. Okay, so basically when we published the paper, we showed that you could actually reduce the latency of a 4 kilobyte row copy by more than an order of magnitude, and reduce the energy, memory energy, by almost 2 orders of magnitude. If you can optimize this, you can easily get to 2 orders of magnitude, in my opinion. It's not that hard. Okay, so that's row copy. And of course, you need to generalize the mechanisms. You need to show that you can do it not inside the subarray, but also across banks. That requires a little bit more hardware support. The paper could not show that, because that requires slightly more hardware support if you want a general mechanism. And you need to do it across subarrays also. And the paper talks about these, and we have other papers that build on top of this as well. Basically, I think the mindset is like this. If you look at this copy operation, this is something memory is very, very good at potentially. We're adding the specialized computation capability in memory based on what the memory is really good at. If you look at the systems that we're designing in a broader perspective, we're adding a lot of accelerators. They're all good. They're all actually specialized for many different reasons. But they're all sitting on this side of the memory bus. There's no accelerator that's sitting on the right side of the memory bus. Maybe we should be putting some accelerators that are sitting on the right side of the memory bus, taking advantage of the huge amounts of data at low latency and low energy access to that data. Right? So essentially, memory is very similar to a conventional accelerator, in my opinion. But we need to actually put accelerators over there on the memory side. Okay, as I said, I maybe cheated. I gave you examples of in-DRAM copy. Zeroing is an example of copy, actually. Zeroing is a special case, or initialization is a special case. Now I'm going to give you examples of actual computation inside memory in DRAM at low cost. Basically, we can use the analog computation capability of DRAM. The idea is very simple. You activate multiple rows that performs computation. I'm going to give you the example in a little bit. And this leads to significant performance and energy improvements, 30 to 60x, in terms of the bitwise operations and or not majority. And I'll talk about this paper. But before I go into how we do it in DRAM, I think there's a lot of opportunity here. What I'm going to show you is just an example. There are new memory technologies like RRAM, STT-MRAM, phase change memory. They enable even more opportunities, in my opinion. Because if you look at DRAM, fundamentally, whenever you access some row, you destroy the row. So fundamentally, you have to move the data out of the cell a little bit to be able to do computation. But some of these actually, most of these emerging memory technologies are non-volatile. As a result, they can operate on data with minimal data movements. Basically, in place, you can do operations. And there are actually works that have been examined that are being published that show that you could do matrix multiplication, for example, inside an array of RRAM cells. And you could do other things also. I'm going to actually reference one of the papers that build on what I'm going to talk about in a little bit. So I think I'm very supportive of the work that's going on in new memory technologies as well as DRAM. I think people should be examining what are the potential limits of how can we do computation with minimal data movement with these new memory technologies. Even though they don't exist, or computation as proposed in the works don't exist, I believe that they're going to exist into the future. And they may actually surpass DRAM because minimal data movement is easier in emerging memory technologies. Okay, so now let me go back to DRAM. Actually, what I'm going to describe is in DRAM, but this is actually done in phase change memory as well. I'm going to reference the work. Essentially, the idea is if you can activate 3 rows concurrently, you can do computation. So I'm showing you examples of 3 cells over here, 3 bits. But imagine that these cells are part of a row, 8 kilobytes. And imagine that there are 1,000 rows, 1,000 different subarrays where you can do this in a single DRAM chip. So it's 8 million bits per cycle in DRAM. Of course, if you design the DRAM to do computation, you could increase that. So basically, the capability of computation grows with the number of cells that you have in DRAM in this case. But let's take a look at a single bit. Now, if you had the permitter to activate 3 rows concurrently, you would activate the 3 rows. All rows get connected to the bit line. And the result that you get on the bit line is a majority function of the 3 rows. Essentially, if at least 2 of the cells are charged, you get the charge state at the end, which is the case over here. If at least 2 of those cells are discharged, you get the discharge state at the end. So this is a simple bitwise majority function. So by activating 3 rows at the same time, you can get a bitwise majority across 8 million bits, let's say, inside a DRAM chip. That sounds nice, right? Now, majority is great, actually. Knuth in his Donald Knuth in his 4th book, I guess, let's say, he talks about the importance of majority function and how you can build things on top of majority. But I think we want to do more than majority. Essentially, if you actually rewrite this Boolean function, if you take out C, if C is 1, you get the OR of A and B. If C is 0, you get the AND of A and B. So you can do bitwise AND and bitwise OR across millions of bits in DRAM. That sounds great. Right? Of course, bitwise AND and bitwise OR, they're not complete logically. If you really want to have a functionally complete engine in terms of Boolean algebra, you want to have a NOT in DRAM. And we add NOT in some way. Basically, we feed the negated value. It actually exists. The complement of a row, complement of a bit exists, but you don't have access to it. Basically, it's on the other side of the sense amplifier. You basically want to connect that to a DRAM row. And if you actually do that with some more hardware cost, you can have the NOT. And once you have AND and NOT, or and NOT, you're functionally complete. Essentially, you can port any algorithm on top of the substrate. Of course, some algorithms are easier to port. Okay, so let's take a look at the performance implications of it. For example, the NOT, the performance improvement is about 50x. The energy reduction is about 60x compared to existing systems. Of course, AND and OR, NAND NOR, XOR XNOR, so you can actually build any kind of bitwise primitive on top of this. Then the question is, of course, which applications take advantage of it? I'm going to give you some examples. These are not comprehensive, but some examples are a better fit in terms of these bulk bitwise operations. Essentially, we have a bulk bitwise execution engine in DRAM. And a lot of databases use bitmap indices, for example. There are some databases that are designed for maximizing these bitwise operations. This is work from Jignesh Patel's group that was published in 2013, at the same time as our paper, actually, as our row clone paper. They basically showed that you could actually design a database to do the queries by maximizing the bitwise operations, and we ported their database in our system, showing some benefits. Microsoft had the same idea. They designed this bitfunnel web search engine to maximize the bitwise operations so that they can accelerate things on GPUs. That's a very good fit also. And there are a bunch of other algorithms that I'm not going to talk about, but we actually have work in the DNA sequence mapping, for example. So, for example, this is one example. If you port some queries that use bitmap indices on top of our substrate, you get significant latency reductions. This is a latency reduction on the order of 5 to 6 or 7x, let's say, in terms of the entire query latency. I'd be happy to talk about this further. We don't have time to go into details. If you actually take a database that's designed to maximize bitwise operations, this bitweaving engine, you get even more performance improvements. Basically, we see performance improvements in terms of, again, query latency close to 12x in some cases. And the good thing is actually the performance improvement increases with the size of the data that you have in this case, because as you keep adding memory cells, you're actually increasing your computation capability. Of course, you need to be able to cool off your memory. So nothing comes at zero cost, right? If you want to do computation in memory, memory is not going to stay like today. Today, you don't put anything on memory. Memory doesn't have a heat sink. Sometimes, for example, people say, okay, you put computation in memory, but you need to cool off the memory. And I say, yes, of course. Yes, you need to cool off the memory because you're doing computation there, right? Okay, so it doesn't come for free. But nothing comes for free in the end. But it does reduce your data moment. And actually, energy benefits are also very high. I don't show them over here, but you can read the paper for more detail. Okay, and that's the paper. And actually, we've recently written with my student whose thesis is on this topic, Vivek Seshadri. He's at Microsoft Research India right now, a long book chapter that talks about this bulk bitwise execution engine. And I like this one because chapter 2 of this one is probably the best the DRAM background that I've ever written. If people are interested in the DRAM background, just read section 2 of this chapter. Okay, this sounds good. Now I'm going to take some time to talk about. How much time do we have, by the way? Until when?
Yeah, I think you're almost 1 hour.
Almost 1 hour. Oh, okay, I see. Then we can take questions even. Okay, I can talk about all of this topic entire day, of course, but 1 hour is better than some other time. Okay, now let me talk about one of the real limiters of why we cannot do this today. And that's going to be talk about mindset. So this all sounds good, no? Who thinks that Mbit is a good substrate? What I described is nice. Nobody. Okay, maybe. Okay, some people do. Okay.
Nice with some limitation.
Not exactly. With some limitations, absolutely, yes. But limitations can be solved over time, actually. So I think this is a good substrate. Actually, I'm going to tell you even more stories later on, but let's talk about this one. So these are some reviews that we received from ISCA 2016. So this is a review, actually quite positive review. This is a very clever, novel idea, and it's actually true. I have never found an idea like this in literature. We did a lot of studies, patent searches, and everything. You cannot find this idea in literature, as far as we know. Great potential speed up energy efficiency gains, but the reviewer goes on to reject this paper, saying that probably won't ever be built. Not practical to assume DRAM manufacturers will change DRAM this way. Now, this is a bad mindset, I will say, because if you actually reject papers saying that something will not be built, you're almost guaranteeing that it will not be built. But if you actually say, okay, this is a good idea, so maybe someone will build it in the future, then you can actually enable the building of it. Basically, it's not a scientific reason to reject a paper. In the end, this is very speculative, as you can see, right? It's all speculation. Okay. But this is really about a mindset issue in the end. So this is a review from ISCA 2016. The paper was not published in ISCA 2016. Yes. Yes.
So how do you write a rebuttal?
You cannot write a rebuttal. Well, you can write a rebuttal that's not effective in the end, because if the mindset is so strong like this, you cannot change that mindset. Basically, you need to educate the community over time, in my opinion. We can talk about that separately. Okay. So another review from the same conference that says, again, very positive review overall. It's very strong, but it says it requires a modification to DRAM that will only blah, blah, blah. Anyway, it's a very similar mindset in the end. I'm going to, actually, these reviews will be rebutted 5 years later, or a few years later after that, because the paper that was published in Micro 2019 from the Princeton group shows that you could actually do some of these operations in off-the-shelf DRAM chips without even doing what we discussed, basically without changing the DRAM chips. And that shows that DRAM is actually almost capable of doing this. If you actually redesign it slightly, you can do even better. Okay, there's another review. This is another problem that is about the mindset, but in a different way. Basically, this person says, I do not find architectural innovation, blah, blah. It's a circuits technique. I'm an architect. Why are you bothering with your circuits technique? I think this is also not a very good mindset going into the future. We really need to think across the stack, basically. We really need to be open to solutions that solve problems with different layers. So you cannot say, I'm a circuits person, I don't care about architecture. I'm an architect, I don't care about circuits. I'm an operating systems person, I don't care about architecture. If you keep doing that, there's no way you're going to solve the problems, because the problems are complex today. It's not going to have a solution at a single layer. Okay, that's why we acknowledge all the places where our papers rejected from in our acknowledgement section. So if you have papers rejected, don't worry. It's happening to everyone in the end. But I think this is not a good mindset. That's why I've been talking about this. I talked about this at ISCA also, actually, this year. I think we really need to change how we think about mindset. And this mindset is even harder, especially in emerging memory technologies, right? Like this, like processing in memory. Basically, we have a mindset issue. There are many other similar examples for many other papers. If you think industry is better, that's not true. Industry is also actually very resistant sometimes. If, for example, JEDEC, which is the standards committee for DRAM interfaces, they're very conservative. I'm not going to talk about that right now. The question is, how do we fix the mindset problem? I believe we really need to keep doing research, education, implementation, and alternative processing paradigms. There's no question about that. We cannot stop because of this mindset issue. We need to work on enabling the better future. So in this case, for example, at some point, we put the paper on archive. It used to be called BuddyRAM. And other people actually started citing the paper and developing the work on top of it. I'm going to show you one example of that paper. One of Yuan Shei's papers actually builds on top of the work. And I believe we really need to be more open in these things. So somehow we need to fix the reviewer accountability problem in our community, because a lot of good ideas are getting rejected in the end. So just like main memory needs intelligent controllers, I believe our community needs accountable reviewers as well. But of course, I think, let me give you essentially 5 years later, this is a paper that was published in Micro 2019. When people were saying that, oh, DRAM manufacturers will never change DRAM. This paper shows that all of the chips that they've tested off the shelf. So they took our SoftMC infrastructure, which we open sourced, which is essentially a DRAM testing infrastructure, and they did it completely independently of us. They basically took the infrastructure that we published online. They were able to test DRAM chips. They modified the timing parameters in DRAM such that they could get row clone to operate. So row clone requires 2 consecutive activates. So if you reduce the timing parameter between 2 activates, you can actually do row clone in existing DRAM chips. And they showed that you could actually do row clone in existing DRAM chips. They actually showed that in a limited subset of the DRAM chips, you could actually do bitwise AND and OR, just like we predicted, by changing the timing parameters. Of course, I don't think this is a proof of concept, in my opinion. This is very good, and people should be exploring this more going into the future. I don't think this is the way to really do computation in DRAM. These are off-the-shelf DRAM chips. They're not designed for computation. But this is a proof of concept that shows that even if you don't design the DRAM chip not for computation, you can still do computation in it. So imagine what you can do if you actually go and slightly change the DRAM chip, just like we said, and do computation in it. Then you could be much more reliable. OK, so this is an example that I believe rebuts the reviewers better than I could. That's the rebuttal. But of course, it's 3 or 5 years later, right? It's not, it's not an effective rebuttal. OK, this is the paper that I mentioned. So this paper was published in DAC 2016. It's from Yuan Shei's group that shows that you could actually do something very similar in phase change memories to do bulk bitwise operations, and even more to accelerate graph processing, machine learning. I think it's a beautiful paper. And they give credit to our work that was on archive because it was rejected multiple times from the review process. OK, has anybody read this book over here? Anybody taken a computer systems modeling, performance modeling class? This is one of the greatest books that I would recommend to people. It's The Art of Computer Systems Performance Analysis by Rod Jane. And I use this book with my students, for example. I like this picture from this book a lot. These are basically some rat holes over here, as you can see. And basically, this book suggests that any idea can be rejected. And it says that even if the performance analysis is correctly done and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. And basically, he goes on, makes a list, a compilation of reasons for rejecting her at various performance analysis presentations. He says that you can use this list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. He also says, the list is helpful in getting competing proposals rejected. Oh, I see that. This is working now. Fine. So I would recommend this book, but because this really talks about the mindset issue. So this is the list of reasons. It's about 26 reasons why you can reject something, an idea. The first one is this needs more analysis. You can reject based on this analysis. And the last one I like a lot because it's really about the mindset. It says, why change? It's working OK. If that's the mindset, there will be no improvement in the world, right? Why change? Everything is working OK. Actually, everything is working OK right now. But 20 years down the road, is it going to be working OK? That's good to question, right? 20 years down the road, will the Earth still be there? I don't know. OK, so I think I will end with a positive note because I think this is exactly what to do in the end. Basically, I think if you're a researcher, I would suggest following your passion. Do not get derailed by naysayers. There will always be naysayers in the end, and that will happen. I would say be resilient. You have to be resilient. If you believe in an idea, you'll be resilient and focus on learning and scholarship to actually show that the idea benefits. And if you put the good idea out, a good idea will eventually be picked up and somebody will use it. Just like these folks that showed that you could actually do this in real DRAM chips today. And I think in the end, the quality of your work defines your impact. I know there are a lot of students over here who are going to present their work. I strongly believe in this in the end. OK, that was my kind of detour into the review process. But I think it was important because in the end, we're going to get back to the mindset issue. A lot of the problems that we have in designing an intelligent architecture is about the mindset as well. OK, let me talk about exploiting 3D stacked memory with slightly less detail, because this is also very important in terms of enabling processing in memory. So we have basically here, we have another opportunity in terms of technology. We have 3D stacking. We can stack logic layer underneath memory layers. And this logic layer is connected with high bandwidth, low latency interconnections through silicon vias, and going into the future vias, much faster connections. Essentially, we could put logic underneath memory that we can, general purpose logic in the end. And other true three-dimensional technologies are under development, monolithic three-dimensional technologies. I believe they're going to enable a lot of interesting system designs into the future. And if you read our Remulator paper, we actually studied the DRAM landscape in 2015, and there were a lot of 3D stacked memory technologies at the time. This is going to increase into the future. So the question is, how can you use this logic layer to do computation? And I believe there are multiple questions over here. I'm not going to cover the entire space, but I'm going to give you examples. And I think there are two. Whenever you have a technology like this, it's always good to ask the question, what is the maximum thing that I can do with this technology, and what's the minimum thing that I can do with this technology? And I'm going to cover both ends. Maximum thing requires, I think, specializing the technology for the application. And we ask that question basically, can we somehow get a lot of performance and energy benefits if we actually use this 3D stacked memory as an accelerator for a given application? And if we had the freedom to change the entire system for this, every decision that we make in the system, we're able to change. Clearly, this is not feasible immediately. But some people may do it, actually, because some people are very willing to change. And of course, the next step is maybe we don't change the entire system, but we change some simple things, like do simple function offloading. I'm going to talk about that also. And the minimal thing is, what is the minimal thing that you can do without changing much in the system? So let's start with this one. I think this is going to be important because it's going to define what are the maximum benefits. And the benefits that I'm going to show you over here are not going to be the maximum, because when we started the work, we were doing the work the first time. Later, a lot of people improved upon the work. So I'm going to show you examples showing that the benefits that we get are about 14x or so in terms of performance. I think the recent papers, for example, Zhuhai from USC has some papers on this topic. Their papers show that you could actually, performance improvements are on the order of 2 orders of magnitude with the additional optimizations that they have added into the system, which are actually very good. So you can actually get to 100x or more. What I'm going to show you is about 14x. Okay. And when we started looking at this work, we said, what are the important applications? And graph processing was very important to us. And I still like it, actually, because it's it's used in many, many systems, clearly. It's used in bioinformatics today. Actually, a lot of genome analysis done on graphs today. It's used in a lot of machine learning frameworks. So there's a lot of applications. And clearly, I put Facebook over here, but China has equivalents of this, which may be bigger. I don't know. When I deliver this talk at Facebook, they always are angry at me, saying that it's not 1.4 billion, it's 2.33 billion. But I don't want to change my slide, so it's good to keep it at 2015. I think China is also close to 1 billion or something like that, right, at this point. Maybe higher, I don't know. But basically, if you have graph processing, scalable large-scale graph processing is very challenging. If you throw cores at the problem, you don't get much performance. If you quadruple the number of cores, your performance benefits are 40%, 20%, something like that. Why? Basically, this is the PageRank algorithm, but a lot of graph processing algorithms are like this. You have frequent random memory accesses, not a lot of locality. There are parts of graph processing that has good locality, and you should exploit locality, but a lot of parts of graph processing have bad locality. And there's little amount of computation to cover for the memory accesses. So this is really an application that really exacerbates the memory access problem, basically data movement problem. You don't get good locality, so your caches are essentially useless for much of the application. But you're doing these random memory accesses that are causing a lot of data movement in the system. So we designed a system that's called Tesseract. I'll give you the high-level overview and the results. I'm not going to go into the details because this is really changing entire design decisions that we have in the system. For example, we don't have cache coherence in this. We don't have a shared memory programming model. It's message passing based. Essentially, you have this logic layer underneath memory layers, and the logic layer is divided into what's called vaults. Each vault controls the memory stack on top of it. And each vault has essentially a DRAM controller. We're going to add a very simple embedded in-order core inside there so that we can do general purpose computation. And these cores are connected to each other via some interconnection network inside the logic layer, so they can communicate with each other. And if you want to scale up the system, you connect these cubes to each other with some other interconnection network. And what you do is, as a programmer, you lay out your graph on top of these cubes, and within the cubes on top of these vaults. And when you lay out your graph, you should be careful. You should partition your graph such that you maximize locality as much as possible, which is an important problem. It's not an easy problem. And some of the work that was done on top of our work showed that if you actually do the partitioning in better ways with better methods, you get a lot more performance benefit, which is great. But you need to partition your graph. And once you partition your graph, essentially what happens is whenever you want to update a graph node, or whenever you want to update a graph node, you essentially send a message to the processor that houses the graph node. Essentially, you don't move the data to the computation, you move the computation to the data. And we took the extreme step, you always move the computation to the data. You could actually optimize the system to do more intelligent decisions going into the future, in my opinion. Essentially, the data is contained in the processor stack, and you send messages. It's all message passing based. It's remote function call based. It's very similar to distributed systems programming. So the programming model is not very unfamiliar to distributed systems programmers. And this is like a distributed system on a chip and across chips as well over here. And we also have some graph processing specific prefetching mechanisms that actually improve performance, because if you actually use in-order cores, they're not able to saturate the entire memory bandwidth on top of them because there's a lot of memory bandwidth. So if you actually use prefetching, you get a lot more performance. Okay, let me give you example performance improvements very quickly. A lot of the details are in the paper in terms of the design. So if you look at existing systems, they all have the processor memory dichotomy. And as a result, they're limited by the bandwidth of the memory bus. So this is hybrid memory cube-based system. The bandwidth is 640 gigabytes per second. Tesseract looks different. There is no processor memory dichotomy because processing and memory are in the same place, essentially. These cubes are connected to each other in some way. And overall, the cores get exposed to 8 terabytes per second memory bandwidth. So it's significantly higher compared to existing systems. And this is the performance improvement that we observed in our unoptimized system. Basically, we get about 13.8x performance improvement average across 5 important graph processing algorithms. But as I said, if you really want to know the state of the art, this was published in 2015. It was rejected twice before it was published, by the way. But fine. It was published in 2015, and recent works in 2019, for example, show benefits going up to 120x or maybe higher. I haven't examined all of them to give you an exact number, but you can take a look at it. And the reason is we can exploit the memory bandwidth, 8 terabytes per second. We can exploit 2.9 terabytes per second. And recent works actually are able to exploit even better. That's why they get even higher performance benefit. And the energy reduction that we reported is actually quite promising also. In our system, we showed that there's more than 8x energy reduction on these 5 graph processing algorithms. And again, recent work showed that this is even higher. So the potential is actually, in my opinion, great. I don't know what's the limit, but I think it's not unreasonable to get to 3 orders of magnitude potentially in terms of performance and energy improvement, maybe combined. And if you're interested, that's the paper that talks about Tesseract. Okay, but of course, this is changing the entire system, right? You get rid of coherence, you get rid of shared memory. It's a very different model for most programmers. Maybe 20 years from now, it may be a common model, but going there immediately is not very easy for most programmers. So then we also examined other approaches to processing in memory. I'm going to talk about the simple function offloading relatively quickly. This is the work that we've done with Google, for example. We wanted to basically understand the benefits of processing in memory in these consumer devices. What can we do more realistically in these devices? And we examined these 4 applications: browser, TensorFlow inference, machine learning inference, and video playback and capture. I think everybody is using these in some form, maybe not exactly these applications, but some form of these applications. And we wanted to understand the energy cost of data movement in these workloads. And essentially, we saw that in common use cases, more than 60% of the total system energy is spent on data movement. And we wanted to get rid of that data movement by moving computation close to data. Of course, the challenge here is limited energy and area budget you have in an SoC that looks like this. So you need to be really careful what you put inside the logic layer, for example. And we wanted to put functions inside here so that we can make this easy to program. So the programmer goes over the code and identifies functions that could benefit from the compute units that are close to DRAM in this case. And it turns out these functions are actually not a lot. Basically, a significant fraction of the data movement often comes from simple functions in these workloads that you really care about. For example, one function is row copy. Another function is initialization, again, row initialization. I'll give you some other functions. Compression is a bigger function, of course. Decompression is another function. Motion estimation in video is another function, for example. Quantization is another function in machine learning inference. It's used in all machine learning inference systems. Quantization, it's very data movement intensive. So the question is, of course, we can offload these functions to low power embedded cores over here inside the memory, or small fixed function accelerators. And we examined both of these options. In my opinion, you should really have some hard units that in the logic layer, also some reconfigurable units, because I think having that reconfigurable units is very important in the logic layer so that applications can customize the logic layer to their needs. And in the end, what the benefits that we see are about 2x. So we said basically you can reduce the execution time by 55% and reduce the energy by 54%. If you actually do the calculation oppositely, you improve performance and reduce energy by 2x. Right? So it's not 13x, it's 2x, but 2x is not bad also. And these are some functions. I'm not going to go into the detail over here, but you can see that in TensorFlow Mobile, when you do in a lot of the networks, deep neural networks, packing of the data is very important. Whenever you move from a network layer to another network layer, you need to reorganize the data in some way, and that reorganization is very data moment intensive. And if you actually have a specialized function that's offloaded to memory, you can actually improve performance by 2x and reduce energy by 2x, meaning halve your energy. And you can see other functions over here, like texture tiling, deblocking, filter in video. Of course, you need to identify these functions, right? But overall benefits are about 2x in the end. And we've been actually doing other research that I'm not going to talk about in improving, in taking advantage of processing in memory GPUs, for example. That's another place where we can actually get a lot of benefits. So you may have a very powerful GPU, but simpler GPUs in the logic layer. And again, do function offloading into the simpler GPUs. We've developed a compiler that can actually do this automatically together with NVIDIA. I'm not going to talk about this. If you actually do this automatically, the benefits are even lower. Why? Because you're not actually designing your program to take advantage of these units. And in this work, for example, we show that the benefits are about 30 to 50%, which is not bad because the programmer doesn't need to do anything here. It's all automatic. And it's a good step towards enabling the adoption of this sort of technology in the end. Initially, you get 30 to 50%. Over time, programmers start programming it, and you get 2x. Over time, maybe you get even more, right? That's the idea. And if you're interested, there is more work. So I think I've already been talking about this, but enabling adoption of a new technology is really important because you can design any hardware you like. In the end, if you don't enable the adoption of it, it may be useless, right? And there are many, many examples of it. My favorite example is Intel IA64, for example, if you remember, the Itanium architecture. I think there are a lot of great concepts over there. It had its impact, but it's not being used at the moment because it's not adopted in a widespread manner. Okay, so and there are many barriers of adoption to a technology like processing in memory. Actually, these could be reasons for rejection of papers also, by the way. I think functionality and applications, software. Essentially, the first part is software. How do you develop the software and enable processing in memory? The second part is also almost related to software, which is programming. What are the programming interfaces? And what is the hardware and compiler support for programming? The third one is system support, coherence and virtual memory. How do you enable those things? The fourth one is also system support, runtime system, compilation, data mapping. How do you map the data? How do you enable easy mapping of data to the programmers? Access and shared control. How do you enable that? These are all very good questions. I'm not going to talk about over here. There are some works that touch upon these issues, but they're not completely solved issues for sure. And the last one is infrastructures. Basically, how do you assess the benefits and feasibility of this with real infrastructures? I believe all of these are very, very important to solve, and all can be solved with a change of mindset. I think the worst part in terms of adoption is the mindset itself. And we're going to get back to this basically. If you change the mindset saying that, okay, this technology is very promising, I'm going to enable it, then you actually go and solve all of these problems. And we've done it in the past. I'm going to give you examples at the very end of the talk. I think we really need to revisit the entire stack to solve the problem. We need to look at all the way from devices to algorithms. And I believe we can get there step by step. So let me talk a little bit about Pim Enabled Instructions over here, because this is the minimal part that I didn't talk about. So what is the minimal thing that you can do to take advantage of this technology? And in one slide, the idea is this. Basically, we wanted to not change the system. No changes to programming model, no changes to coherence, no changes to virtual memory. Can you still take advantage of processing in memory with 3D stacked memories? And the idea is very simple, in hindsight, in my opinion. Each PIM operation is an instruction. And this instruction is virtually addressed. It's executed in the host to begin with, and it operates on a single cache block. So you actually do operations on only a single cache block. This gets rid of the data mapping problem. So for example, it's a Pim add instruction. So this doesn't have any changes to the sequential execution and programming model. Your compiler can emit these instructions. No changes to virtual memory. Very little changes to the cache coherence. They're relatively easy. No need for data mapping. So actually, it's very adaptable in my opinion. The second key idea is, of course, where do you execute this instruction? The processor fetches this instruction. It has to make a decision. Should I execute it in the processor? Should I execute it in memory? So you need to have some heuristics to be able to do that. I'm not going to go into a lot of the details, but I'm going to show you an example of the instructions. This is a Pim add, for example. This is PageRank in graph processing. And we have some fences to ensure that Pim operations are done when you get to the fences. That's fine. But these are some example instructions that we have designed, customized to the architecture. For example, we have a dot product instruction for machine learning, Euclidean distance operation for streaming data analytics, histogram operation, hash table probing, floating point add. So you can actually, if you have a reconfigurable logic layer, you can actually imagine a lot of really interesting things over here. Basically, you can customize these instructions. And I think this is a very good direction in terms of customizing the instruction set to enable execution on processing in memory. But let me give you the results. Basically, the results are not bad. Essentially, if you go and do this, on large input data sets, we get about 47% performance improvement averaged across a bunch of different workloads, data-intensive workloads, machine learning, graph processing, some database workloads like hash join, for example, and histogram. So it's not bad in the end. It's not 13x, clearly, but this is a minimal approach. And the performance energy reduction is also not bad. You get about 25% energy reduction in a single node when you have large input data sets. Of course, when you have medium input data sets, you still get performance improvement. When you have small data sets which fit in your cache, you don't get benefit. And that's expected, right? The processing in memory or processing near the data provides you the most benefit when your data sets are large and you're operating on lots of data in the end. Okay, if you're interested, this paper has more detail. But again, this is an example of getting there step by step. Maybe you don't change the entire system to begin with, but step by step we examine these issues. I believe we should really be exploring the space very heavily to enable technologies like this. And if you're interested, actually, we've recently written these articles that cover the entire space and talk about some issues that need to be solved to enable to make these architectures more practical. And this is the latest one, actually. It was invited by IBM Journal of Research and Development. They had the special issue on hardware for artificial intelligence. And I believe actually processing in memory is a great fit for machine learning workloads. And we've shown it. Other people have shown it also. And that's one of the reasons they invited us to write this workload-driven perspective article that talks about some of the adoption issues. Okay, so I think this is a challenge and opportunity for the future. How do we design computing architectures with minimal data moments? And that was this first part of the talk. Now I can move to the second part, but these parts are going to take less because I think there's less work in these areas. And we still have time, right? Yes. Okay. Any questions over here? I can take questions at the end also. Yes?
I want one question about the long work.
Yes.
So because you directly move the data from one different row to another different row. But in typical case, when you actually do some memory move to memory copy, you usually require some follow-up processing of the data. This requires you load the data from the DRAM to CPU cache.
Yeah.
So does this mean that it's not very easy to use the cache locality?
We consider that in the paper, actually. It's not, certainly if you always do it in DRAM, you don't exploit the cache locality. Yeah. But you can actually minimize, if you're operating on the entire row, it may make sense to bring it to cache. But if you're operating on a very small part of the destination row, then you just bring that part in the end. So you can actually minimize the data moment. Actually, I think overall a better system design is doing it on the memory side and bring it into a computation unit that's close to the memory. Yeah. So in the 3D stack. But I think your point is well taken. If you need to be very cognizant of the data locality, because if you always do row clone inside memory, you lose performance in some applications. And we show that in the paper.
Okay. And one another comment about the Pim or probably codec, real data processing is that I think in industry the NRMP, I think the standard organization, they are actually organizing kind of a working group to define the system interface for real data processing. I think it's probably not just in memory, but adding some processing capabilities close to the storage.
Yeah.
SSD, maybe some networking.
Yeah, absolutely agree. Yes. So that's why I said the memory side is a bit harder. The industry is certainly looking into SSD and networking side because the interfaces are a bit easier over there. Certainly. Yes. But I think memory is also going to happen into the future.
Okay. Yeah, looking forward to that.
Okay. Thank you. Okay, maybe I'll go ahead and feel free to ask questions later. I'll be here today and tomorrow. Okay, the second part, if you recall, we said that today's architectures are not good at exploiting the data and metadata, a lot of data that's available to them. They make human-driven decisions as opposed to data-driven decisions. So I'm going to give you examples of how we can fix that, potentially. I call this exploiting data to design intelligent architectures. And as I said, in the end, the architectures we design today are very much human-driven. A human goes ahead and designs the caching policies over here, and they remain the same during the entire lifetime. They don't adapt to the workload. They don't learn from what's happening. So this is very dumb, actually. It hasn't learned anything. A lot of stuff happened over the course of even the last minute. It's still doing exactly the same thing in its memory controller. Right? It sounds very bad, actually. I feel sorry for it. Actually, we should feel sorry for ourselves probably, because we're using these devices that don't learn anything in the end. So humans designed the policies, how to do things. As a result, we have many simple, short-sighted policies all over the system. I would call some of them too simple. There's no automatic data-driven policy learning. In fact, there's almost no learning. You cannot take lessons from past actions. Now, this has changed slightly in some parts of the hardware design. Like some of the processors use perceptron branch predictors, if you've heard of that. Perceptron is a very primitive form of learning. It's actually the first model that was developed to model a neuron. And they're in some processors, not in all processors. So they have some learning. So that's why it says almost no learning over here. But we really need to rethink the entire system to be much more intelligent, I think, going into the future. Essentially, the question is, can we design some fundamentally intelligent architectures? So what does an intelligent architecture look like? I believe it needs to be data-driven. Basically, the machine learns the best policies and adapts the policies, changes the policies over time, how to do things. As a result, hopefully, we will have sophisticated, workload-driven, changing, far-sighted policies. And this is really automatic data-driven policy learning, hopefully online policy learning, because in the end, online learning is what's important, right? Offline learning doesn't buy you a lot, as I'll show you in a little bit also. Essentially, I think of all controllers as intelligent data-driven agents. Let's say human beings, or maybe more intelligent than human beings, right? Hopefully, right? We don't want to replicate ourselves also. So the question is, how do we start? Let me give you an example from our experience. And we call this the self-optimizing memory controllers. We did this work actually when I was at Microsoft Research in 2006, 2007, and the paper was published in 2008. And we were very focused on the memory controller. Essentially, the question, if you look at a memory controllers today are very difficult to design. Basically, memory controller receives requests from different cores and basically schedules requests to memory to maximize performance. We're going to focus on performance. Even performance is not easy to begin with. So why are these memory controllers difficult to design? It turns out there are many things that you need to think about when you're designing it as a human. And actually, I was designing these controllers. Other people were designing these memory controllers. I guess if I have time for a story, I'll tell the story. Does anybody know the name Chuck Thacker? Chuck Thacker is a Turing Award winner in 2009. He was at Microsoft Research. He was a technical fellow, actually. He designed the very early personal computing systems, like Alto computer, if you know about that, in 1960s. So he's a great system designer that enabled a lot of innovation in virtual memory and all of that stuff, basically, in the end. So he was actually doing the design for the DDR3 controller for the B3, Berkeley Emulation Engine board on an FPGA. And we were having conversations because I was also working on memory controllers at the time. I'm still working on memory controllers. But basically, he was saying this is the worst thing he has designed in his life. This is coming from a system designer who's designed some of the most sophisticated systems in his lifetime. And I agree with him, basically. In the end, memory controllers are really very bad things to design because you need to consider so many things. Like actually 50 doesn't do justice to it. There are more than 100 timing constraints in DRAM. You need to obey all of them for correct operation. You need to keep track of many resources: channels, banks, ranks, data bus, address bus, row buffers. Now they're introducing even more bank groups. So all of those you need to ensure the memory controller keeps track. You need to handle DRAM refresh on top of this. And DRAM refresh has some elasticity in it to make sure that you can actually improve performance. Oh, we have only 5 minutes? Okay, I'll go much more quickly now then. I thought you said that we had 1 hour. Okay, I'll go quickly. Basically, memory controllers are difficult to design. I'm going to skip these. Why are they difficult to design? You can take a look at these pictures. And memory controller design is actually becoming more difficult because you need to consider a lot of these different devices. You need to consider these different memories, and you're basically stuck in the middle. So the reality is that it's difficult to come up with a policy that's good at, let's say, even performance, not even talking about quality of service energy. There are just too many things to think about for a human. And the workload continuously changes, and the system continuously changes. Forget about adapting. Coming up with a single static policy is difficult. So wouldn't it be nice if the DRAM controller automatically found a scheduling policy of its own? And this is the idea of self-optimizing memory controllers. Essentially, we're going to use machine learning. It's difficult for humans to do this. So why don't we have a memory controller that uses machine learning to adapt its policy? And the observation is that, then the question is, of course, what is machine learning that you use? And we found out that reinforcement learning maps very nicely to memory control in this case. Memory control is a reinforcement learning agent. It dynamically and continuously learns the best policy over time. And if you know about reinforcement learning, the basics of reinforcement learning, actually all of us are reinforcement learning agents. We actually interact with the environment. We observe the state. We take an action. and we observe the reward we get from an action, right? We put our hand on the stove, not a good idea, right? We quickly learn that we don't do that again, right? So essentially, we're going to do the same thing with a memory controller. Memory controller observes the state attributes of its system. It takes an action, and it gets a reward. And over time, it figures out at what state, which action it should take that maximizes the long-term reward value that it gets. Of course, you need to design the system to be able to do that. I'm not going to go into the details of how you do that. We put hardware support in it. Clearly, this is all done in hardware. And you need to be careful in terms of the hardware is designed. But if you designed it nicely, which is written in this paper, basically the designer, what does the designer need to do? The memory controller clearly now figures out the policy. So the policy learning is not designer's job, which is nice. But the designer needs to specify the reward function, which is really important, and you need to be extremely careful. I think this is the hardest part. The designer needs to specify the actions. That's the easy. Hopefully you know what actions you're going to take, although there's some trick you need to play. State attributes is hard. Which state attributes should you consider as a machine learning agent? It's always a problem in machine learning, but I believe these can be learned also. And there's a lot of work in machine learning recently that looks at how do you learn the state attributes from your environment continuously. So I think this is possible to learn. This is not easy to learn. This has to be designed. I think the hardware designer's burden is really over here and perhaps slightly over here today. But if you actually do it, our work shows that you can actually get large, robust performance improvement over many human design policies. Even with offline learning-based policies, we get more than 20%, about 20% performance improvement, basically. Of course, this performance improvement increases as your bandwidth becomes a bigger bottleneck. Okay, so basically, you get continuous learning, reduced designer burden, but there are, of course, downsides to it. How do you design different objectives, hardware complexity, and, in my opinion, design mindset as flow. I think this is something that we should discuss because this is something that needs to change to enable these intelligent agents. Hardware design mindset is very fixed today. You design a policy. To test it and verify it, you need to know how the policy works. But here, you have a black box. How do you test it? How do you verify that black box? So all of the hardware design flow needs to change to enable something like this. Okay, so if you're interested, this was published in ISCA 2008. I'd be happy to talk about more. There's a lot more interesting things to be done. Basically, we really need to rethink the design of all controllers that we have in the system to really take advantage of the benefits. So this is, somehow we need to enable self-optimizing or data-driven computing architectures. Now, let me very quickly spend a couple of minutes on this one, and then we're going to conclude. Basically, the last one is about data-aware architectures. Today's architectures are component-aware. They're not data-aware. What does this mean? Data-aware architectures understand what it can do with and to each piece of data. So data is very important. We're data-centric, if you remember. And we want to know what we can do to the data. Basically, we want to know the properties of the data and the requirements of the data so that we can improve performance, efficiency, and other metrics. For example, you can imagine many properties of data. How compressible it is, how approximable it is, what is the locality characteristics, what are the sparsity characteristics, what is the criticality characteristics, what is the access semantics, what is the security property. So there are many, many properties of data that you can specify. It's endless, actually, over here. This is just our imagination over here. But what do we do today? In general purpose architectures, you don't communicate any of this to the hardware or the system. The system is not aware of these properties. The system discovers it sometimes, the locality properties, for example. But what we do is basically we have all this rich information at the higher levels. The programmer knows a lot. Sometimes the compilers know a lot. The system knows a lot, actually, over here. But we funnel that through a very simple ISA into instructions and memory addresses. Of course, there's effort in terms of actually changing this. But in general purpose architectures today, we're not there yet. In some, there are very simple examples of instructions that communicate some information, but they're very specialized cases. So the question is, can we design a general interface to enable the communication of all of this rich, high-level information to the lower levels of the system as well as the hardware so that we can actually exploit these semantics that are visible at the higher levels? Again, I'm not going to go into the details. We call this expressive memory. Actually, we have some, this paper actually talks about it. But I'm going to give you some examples. This is a table from the paper that shows that if you actually, for example, know the compressibility properties of different data, you can adapt the compression policies nicely. For example, if you know the data type, if you know the sparsity of your data, then you can adapt the policies that you use inside the hardware. Of course, you can potentially discover some of these characteristics underneath, but discovery is actually complex. There are other examples. Approximability characteristics is another example. You can distinguish different types of data in terms of approximability. I'm not going to go into the details more. You can read the paper. And we've actually done another example of this with NVIDIA, just in terms of locality. If the programmer can convey the locality characteristics of the data, inter-thread locality, intra-thread locality, what is the characteristics of different NUMA locality, you can actually place the data and place the threads underneath, inside the hardware in a much more intelligent way. And as a result, you can improve performance significantly. We call this a locality descriptor, and NVIDIA is actually using this in systems going forward. So there are other examples of this actually in hybrid memory management. For example, if you actually have different types of memories with different characteristics, you really need to know the characteristics of your data to take advantage of a system like this so that you can achieve the best of multiple technologies. Let me give you one example. This is a work that we've done with Microsoft that shows that you could actually improve the cost of your data center if you know the approximability or error characteristics of your data. Basically, this is the error vulnerability. Some data is very vulnerable to errors. If you get an error in the data, the system crashes. Some data is not vulnerable. If you get an error, it's not that important. Now, if you can actually identify this and communicate this as vulnerable data and tolerant data, you can design different types of memory in your system, low cost and reliable. Low cost is very simple. Reliable is expensive. And we call this heterogeneous reliability memory. You can actually reduce the cost of your system or improve the performance or basically optimize different metrics. In this work, we showed that you can get rid of a lot of your error correcting codes in your system because most of your memory doesn't really need to be reliable, actually. You just need to be very careful what to place in your unreliable memory. And if you do that, you can get rid of most of your ECC in your memory. Most of your memory can be very low cost, and you can get rid of the data center cost by about 4.7% while keeping the reliability requirements that you have in the data. Very quickly, another example, if you know the data properties of different layers, for example, in your deep neural network, you can map the data to different types of DRAM, like DRAM with reduced latency and reduced voltage, or you can dynamically change the latency and voltage of your DRAM while still achieving a user-specified accuracy targets in your deep neural networks. And this is essentially this is data-aware management of DRAM latency and voltage for deep neural network inference. Again, I'm not going to go through this in detail. The key idea is map more error-tolerant DNN layers to DRAM partitions with lower voltage and latency, and you can partition your DRAM to have different maximum tolerable bit error rates. But you need to be able to map your data carefully to these different DRAMs that have different error rates in the end. And in this work, we showed that you could actually do this relatively easily in existing systems with 4 DRAM partitions. Okay. And you get performance and energy improvements that are significant in the end. Okay, but all of this comes with an expressive architecture where you can communicate the requirements of the data into the underlying architecture in the end. Okay, now I'm going to conclude. So, basically, this is a recap. These are the architectures that we designed today. I'm not going to go over this, but I think we can design much better architectures for intelligent machines that are data-centric, data-driven, and data-aware. Now, if you have 2 minutes, I'm going to talk about the fun part of the talk, as usual, because I think this is, again, about the mindset. There's a famous architect that said architecture should be based upon principle, not upon precedence. And I believe these are actually principled designs going into the future. And this famous architect was Lloyd Wright. And he built not this, because it's a precedent-based design. It's not bad. It works, right? You can live with it. But based on his principle, he designed this, falling water. If the mindset was, this works okay, why change? He would not design this, and the world would be a different place, right? Basically, this is extremely costly, clearly, compared to that previous one, and people paid the cost to transition to the new technology based on some principle. Okay, and there's some principle over here. So this is a train station that's a precedent-based design. It's all over Europe. Now, I use this example also in my classes. And if you look at this, it's not bad. It works. Why change? It works okay, right? But some other architect then came and said, OK, pay me some money, and I'm going to give you a principal design. And the principal design is this. This is Bahnhof Stadelhofen in Zurich. It's high cost, but it's a new technology. But now that you've adapted the new technology, the cost is not important. This, now 20 years later, 30 years later, nobody cares about the cost of it. They just enjoy the new technology, right? That's the idea. This is also another GAR in Lisbon. This is close to where ISCA is going to be next year in Valencia, from the same architect, City of Arts and Sciences. This is an example that I like because this is in New York. This is the Oculus. New Yorkers paid apparently $4 billion for it, and they were extremely angry. Some of them were extremely angry because of this. But this is new technology. Now nobody cares about the cost of it. Actually, probably it makes up for its cost. And in fact, I was recently in Yungang was taking me around the bird's nest in China. I didn't do my research, sorry. I should do my research so that I could change my slides over here and add the bird's nest. But bird's nest is another example, in my opinion. It was designed by Swiss architects, actually. And if you think about this, I don't know the story, but clearly it's very costly in the end. But I heard that it already made up for its cost over time, right? So a transition to new technology is costly, no question about that. But it gets you to a better place. It's painful. You have to pay something to get to that better place. But over time, it makes up for its cost. And this is the architect, Santiago Calatrava. He's an ETH alumnus, by the way. And that's the principle for this one. So the question is, do we have overarching principles for computing? I don't believe that. I don't think I have the principles. But I know that processor-centric design is not the only principle. Or human-driven design is not the only principle, right? I think we should really be exploring the new principles. And I'm not suggesting this is the machine that we should build going into the future. But there are some good things about this machine that we can potentially understand, right? For example, the example that I gave, we can quickly learn from things. We don't need to sift through a million cat pictures to differentiate a cat from a dog, right? So we need to be actually understand some of the principles, perhaps, and do better principled designs. So essentially, I believe it's time to design principled system architectures to solve the data handling or memory and storage problem. We need to design complete systems to be truly balanced, high performance, and energy efficient. And I think this requires intelligent architectures. And again, in my opinion, an intelligent architecture has three principal properties. It needs to be data-centric, data-driven, and data-aware. And if you come up with another property, please let me know. I believe this can lead to orders of magnitude improvements. I've given you some examples of these orders of magnitude, and other works have shown improve our work, as I said, and it increased the orders of magnitude. It can enable new application and computing platforms. Genomics platforms are an example, in my opinion. But there could be other things that clearly we cannot guess now. It can enable a better understanding of nature, in my opinion. Very quickly, psychologists in the 1990s, they thought that computing would be a good paradigm for understanding humans. And if you read psychology books during that time, I took psychology during that time, actually. That was one of my majors in college. During that time, they basically said, computing is a good paradigm for understanding humans. They don't say that anymore because they figured out how computers work. And computers don't work anything similar to humans in the end. So you cannot use computers to really understand humans. But maybe if we actually change the principles that we have, we could get closer to the nature itself, and we could understand the nature much better by building devices that are closer to the nature. I think this is the whole premise of neuromorphic computing, for example, but I think we need to make it more general going into the future. And who knows what else can we achieve if we actually enable more principled architectures. Okay, but maybe we can get something closer to this. But I think to be able to do this, it will come at a cost. We need to think across the stack, but we can also get there step by step. And these are some principles that I'm not going to go into right now. We've covered all of this, actually, in this lecture. But I think most importantly, we really need to have open minds into the future so that we can enable the solutions to this. If the New Yorkers, for example, did not have the open mind and said, we're not going to build this Oculus over here, they wouldn't have Oculus. China wouldn't have bird's nest. Of course, these are simple examples, architectural examples, but they're real examples that enable other types of innovation also in the real world, right? And I'm going to finish with these papers that we've written. And this is an old slide. I have other students who unfortunately couldn't make it to the slide because I wasn't able to update my slide. But I acknowledge all my students and collaborators who had efforts that went into this work clearly. And I acknowledge all the funders. Please keep funding. And my group as well. Okay, thank you. I'd be happy to take more questions.
Yeah. You answered exactly your timeline. And we only have time for one question. Time for one question.
Great talk.
Thank you.
So I like the principle very much, like data-driven, data-centric, data-aware. This also reminds me a little bit about like the data flow architecture and data flow programming models, which also is kind of data-centric, data-aware. So I'm wondering what would be the synergy between processing memory with the data flow architecture.
No, that's a very good point. I think there's synergy, but it's not. I think data flow doesn't encompass everything over here, but it's synergistic in the sense that data flow also puts data into the center of things, right? In the sense that everything happens when the data is available. So the synergy is there, in my opinion. You operate on the data, and data available to also determines your computation in the end. So I believe data flows are a very good fit for minimizing data movement in the end. And also you can burn a data flow engine inside the memory as well. So I believe there's synergy for sure.